Welcome to the Deep Dive. You're probably here because, well, you want to get a handle on important topics, but maybe without drowning in information.
Exactly. We try to give you that shortcut to being well-informed.
And today we've got a really interesting source. It's a description of something called a contact simulator. It was actually put together during the COVID-19 pandemic.
Yeah, and it offers a surprisingly clear window into some basic ideas about how infections can spread. It's not your typical dense study.
Right. So our deep dive today is going to explore this simulator, how it models contact transmission, and what it might suggest about things like social distancing or people recovering.
Mm-hmm. The source mentions it uses a graphics window within something called PowerBasic, a programming environment.
Okay, so a contact simulator.
Yeah.
Let's unpack that. In simple terms, what are we actually looking at here?
Well, imagine a kind of miniature world. The simulator tracks interactions between virtual people inside these virtual houses or social bubbles. And it monitors when they get close enough to potentially pass on an infection. The aim is just to see how it jumps from person to person.
And the setup described starts pretty small, right? 5 houses, 10 people in each.
That's the initial one, yeah. 5 houses, 10 people each, and it kicks off with just 2 individuals already infected.
And it's visual, which I think is key here. It's not just abstract numbers. The description says houses are like polygons, and the people are moving circles.
Exactly. Little dots moving around in shapes. Uses a graphics box control, apparently, with rounding for the circles. It gives you the sort of animated view of potential spread.
It sounds like a way to make these epidemiological concepts a bit more intuitive.
That's the idea. It helps grasp the dynamics without getting lost in really complex math.
Yeah.
So our mission today really is to see what insights this simplified model offers about spread, about interventions.
Right. Building that intuitive understanding from a basic model. Okay, so let's get into it. What did that very first simulation run show?
Okay, so the first run was set for a virtual week, 7 days. And crucially, in this version, if a virtual person got infected, they stayed infected. No recovery.
Ah, okay, so just accumulation.
Right. And what they saw was, well, pretty rapid spread. People are moving randomly, bumping into each other virtually.
And it takes off.
Yeah. The notes mention most initial infections popped up in the brown house, I guess they color them. Then it spread to the green, and later the light blue one.
You can sort of picture it, can't you? These dots mingling, and one infected one touches a healthy one, and boom. And since nobody gets better.
It just snowballs. It's a really clear visual of that sort of exponential growth when there are no brakes on the system.
That really highlights why early intervention is so critical in the real world, doesn't it? One case becomes many very quickly.
Precisely. It shows that potential for a fast ramp up. What struck you about that initial result?
Just the speed, really, and how it seemed localized at first, maybe in 1 or 2 houses with the initial infections, but then it jumped. It didn't stay contained.
Makes sense. Random movement means eventual contact between groups.
Now, the person who built this didn't just run it once, right? They tweaked the parameters.
Yes, and this is where it gets quite insightful. They could change things, like they increased the number of people per house to 20.
Okay, so more crowded virtual houses.
Yeah.
What would you expect that to do?
Well, more people in the same space. Yeah. Intuitively, you think more interactions, right? More chances for transmission.
Yeah, feels like higher odds. More bumping into each other.
And the simulation likely showed that. But they also added something really key, recovery.
Okay. People getting better.
Exactly. They said it. So an infected person was only infectious for like the equivalent of 2 simulation days. Then they recovered and couldn't spread it anymore.
That sounds like a game changer for the simulation's outcome.
Totally. Because now you don't just have infections adding up. You have people leaving the infectious pool.
So you could actually see numbers go down.
That's what the source describes. In the blue house, which got hit hard initially, the infections peaked and then started to decline as people recovered.
Interesting.
And meanwhile, the spread to other houses, like that brown one, seems slower in that particular run. It really shows how the duration of infectiousness matters hugely.
It limits the window for the infection to jump, doesn't it? Before the host is out of the game, so to speak.
Precisely.
Now, there was another tweak mentioned delaying the start of transmission. Why do that?
Yeah. That was quite clever, actually. It adds a bit more realism. If infection spread instantly on first contact the moment the simulation starts,
it might unrealistically infect everyone in the starting house immediately.
Kind of, yeah. By putting in a slight delay, like half a virtual day, it let the little dots move around a bit first. spread out within their house, maybe interact more naturally before transmission kicked in.
Okay, so it prevents that instant, unrealistic saturation right at the beginning. Makes sense.
Yeah.
It mirrors reality a bit better, takes time and interaction.
Right.
Let's talk about social distancing. That was obviously huge during the pandemic. How did this simple simulator illustrate its importance?
Well, the source explicitly points this out. It visually showed why keeping distance matters. Apparently, there was a scenario where the folks in the brown house managed to avoid widespread infection, at least initially.
How?
Simply because, by chance, in their random movements, they happened to keep more distance from the infected individuals, fewer close contacts.
So even without them trying to social distance, just the physics of random movement sometimes created enough space.
In this simplified model, yes. It reduced the probability of those close interactions needed for transmission according to the simulation's rules.
That really drives home the basic principle, doesn't it? Less proximity, less opportunity to spread.
Absolutely. It gives you that gut feeling for why it works.
Okay, so they also cranked things up further, made it even more crowded.
They did. Another run increased it to 25 people per house. And they started with more initial infections, 5 people, spread across 2 different houses.
Okay, so more density and more starting points for the fire. What happened then?
Well, pretty much what you'd guess. A much, much faster and wider spread.
Across all the houses.
The description says infections rose very quickly and hit all the houses relatively fast. Except, interestingly, the red house initially. Apparently, it was the most physically distant in the layout.
Geography still playing a small role even here.
But the main takeaway was clear. More crowding equals quicker, more extensive spread. It really reinforces that link between population density and transmission speed.
More virtual bodies packed in, more starting infections. Yeah, perfect storm for rapid spread. Highlights the risks of crowded spaces.
Definitely.
Now, moving beyond just watching the dots, the source mentions the technical side a bit, PowerBasic graphics commands. Why is that interesting for us as non-coders?
Well, I think what's fascinating is seeing how relatively simple tools can model complex things. You don't always need a supercomputer. It mentions using things like user-defined types. Basically, ways to define what a person or a house is in the code. And arrays, which are like lists, to track everyone's status: infected, healthy, recovered, and their position.
And adjustable constants. Those were the things they tweaked.
Exactly. Things like the number of houses, which was fixed at 5 here, apparently because of the number of colors they used, a practical limit. But also people per house, simulation speed, infection distance, duration, initial infected count, recovery time, all adjustable.
And this whole thing was built with, what, about 500 lines of code? That seems remarkably small.
It is quite compact, yeah. That's a key point. You can get meaningful insights sometimes without massively complex code. It demonstrates the principle effectively.
And it even specified the infection chat.
It did. The description mentions the infected routine gave a 1 in 20 chance of infection upon close contact, a concrete rule within the simulation.
So this basic model, built with relatively simple tools, still manages to show these fundamental principles of transmission pretty clearly.
Yeah, it's like a mini laboratory. You can see things happen that are harder to isolate and observe in the real messy world.
How does this connect then to the bigger picture, to real-world epidemiology?
Well, even though it's simple, the core concepts are there. Contact, transmission probability, the impact of density, the effect of recovery or removal. These are foundational elements in much more sophisticated models that scientists use.
So it helps visualize why public health measures work.
Exactly. It gives you that intuitive grasp of why things like distancing or isolation are recommended. They directly interfere with these basic mechanisms of spread that even this simple simulator captures.
Okay, so wrapping up this deep dive into the contact simulator, what are the main takeaways for listeners?
I'd say first, just how visually powerful it is for showing rapid spread in a connected group, especially with those checks like recovery. That initial run was stark.
Right.
Second, how changing parameters density, recovery time really shifts the outcome. It shows these factors are crucial levers. Third, it provides a really clear, basic illustration of why social distancing works. Fewer contacts equals less transmission. Simple, but effective.
And the crowding effect.
Yeah. Fourth, that crowded conditions generally lead to faster, wider spread. Again, intuitive, but seeing it simulated drives it home. And maybe a fifth point is the technical insight you can model complex dynamics with relatively simple code sometimes.
So a simple PowerBasic simulation, but with some pretty profound, or at least foundational, insights into disease dynamics.
It really does bridge that gap. And maybe this leads to a final thought for you, the listener.
Good one.
Well, think about the real-world situations you see. A busy train, a packed shop, maybe a sparsely populated park. How do the simple dynamics we saw play out in this simulator, the importance of distance, density, contact time, how might those relate to the risks in those much more complex real-life environments?
It makes you think about those background factors.
Exactly. Even a basic model like this prompts you to consider the mechanics of spread and maybe evaluate situations and the effectiveness of different strategies with a slightly sharper eye.
Thanks for taking this deep dive with us.
Absolutely.
Until next time.
See you then.